Hi everyone, this is Mrs. GA, and today we're going to keep learning about solving trigonometric equations. So last class we learned two different methods for solving. We learned that you can try to isolate the trig function and then use the inverse trig function to help you finish solving. And we also learned that another common method is to factor them and then use the zero product property, and then essentially you're going to use the inverse again. So today we're going to learn two more methods and then an additional type of equation. So method 3, again, and it just depends on the type of problem you're given, is to use a trig identity to help you rewrite the equation in a more useful way. So if you look at this problem, we have 1 plus sine of x equals 2 cosine squared of x. So anytime you have two different trigonometric functions, you may want to ask yourself, is there a way that I can rewrite one of them in terms of the other? And we know that there is a way to rewrite cosine squared in terms of sine. So we can use that Pythagorean identity, which is sine squared x plus cosine squared x equals 1. We know that cosine squared of x is equal to 1 minus sine squared. So I can substitute that identity. So when I do this, the equation is now much easier because at least it's a single identity. So from here we can distribute and we can look at what we have to work with. So this looks like it could be a quadratic type equation. So I'm going to set it equal to 0, and then we're going to see if we can factor one of the methods we learned in the last lesson. So I'm going to add negative 2 sine of x to the other side. And here, this is something that we can factor. So here we get 2 sine of x minus 1 times the sine of x plus 1 equals 0. And now here we can use the zero product property. So the sine of x equals 1/2, and the sine of x equals negative 1. Now it's time for our inverse function. So x equals the arc sine of 1/2, and x equals the arc sine of negative 1. A quick reminder, the range of arc sine is negative pi over 2 to pi over 2. So here, this gives us a value of pi over 6. And this gives us a value of negative pi over 2. So remember, if you are using arc sine, the range is from negative pi over 2 to pi over 2, which is why we are going backwards in the negative direction. However, while arc sine can only give us one specific answer, we know that there are other answers that work for this equation. So you kind of have to ask yourself, what other angle has a sine whose value is 1/2? So we know that in addition to pi over 6, this occurs here at 5 pi over 6. And we know that in one full rotation, sine is only equal to negative 1 right here. So whether you want to call that negative pi over 2 or perhaps 3 pi over 2, either way works. Now this is kind of a unique problem because if we actually combine these into a single axis, here's we'll call it 3 pi over 2, which is coterminal, so the same answer. You'll notice that the distance from here to here is 4 pi over 6, which is 2 pi over 3. Same as the distance from here to here, and same as the distance from here to here. So we can actually write all of these angles as one succinct answer. We could just say pi over 6 plus 2 pi over 3n. And there you have it. Okay, let's try another one where we can use a trig identity to help us. So here, again, we have this issue of when we have two different functions, so that's never good. So I want to try to rewrite one to help us with that problem. And so here you might notice that we can actually use our double angle formula. So the double angle formula for sine was just 2 times the sine of x times the cosine of x. Remember, if you ever forget your double angle formulas, you can just do the sum formula. This would just be the sine of x plus x, and you would get the same thing. Now here, this is a method we talked about in the last lesson. Here you can see that we can actually factor this using a GCF. of cosine of x. That leaves us with 2 sine of x minus 1 equals 0. And now we can use zero product property. And we will isolate our functions completely. And now we can use our inverse function. So x equals arc cosine of 0, and x equals the arc sine of 1/2. Okay, here we get x equals pi over 2 because the cosine of pi over 2 is 0. And here we get pi over 6 because the sine of pi over 6 is 1/2. Now let's see where these angles are falling and what other answers might work. So again, our inverse functions can only tell us one answer because of their restricted range, but we know that there are actually other answers that could work. So here's pi over 2. And we know that another angle that could work is 3 pi over 2 because the cosine of 3 pi over 2 is also 0. So you'll notice that these are exactly pi units apart. So we can write this answer as x equals pi over 2 plus pi times n. And then here, again, we get x equals pi over 6. So that occurs in quadrant 1, which of course is the only answer that arc sine can give us, but we know that there's other angles whose sine is 1/2. So sine is also positive in quadrant 2, so we have 5 pi over 6. And again, there's no consistent distance here, so we actually have to write them as two separate answers. So we have x equals pi over 6 plus 2 pi n, so that's going to reoccur every full cycle. And then the last part, we have to say x equals 5 pi over 6 plus 2 pi n. And there you have it. So again, using our trig identity for the double angle identity, that allowed us to kind of work with our equation, and we could actually factor it and finish solving from there. All right, so go ahead and pause the video and give this one a try, and we'll check your answer in just a few seconds. Okay, so here you can see that we can use our trig identity, our Pythagorean identity, to rewrite sine squared as 1 minus cosine squared. So this allows us to turn this into an equation that can actually be factored. So here are factors, and we end up with this. So here, the arc cosine of negative 1/2 is 2 pi over 3. Remember, the range of arc cosine is 0 to pi, so it must be 2 pi over 3. But we know that cosine is also negative in quadrant 3, so 4 pi over 3 would also work. Since this isn't a uniform distance between the two, we have to name them separately and then just say they repeat every 2 pi units. And then here, arc cosine of 1 is 0, and that reoccurs every 2 pi units. Okay, our last method for solving trig equations is to square both sides. So this is just a method you just need to know. It's a technique you need to know. It might not be as intuitive as some of the other ones. So here you can see that we have an equation with two different trig functions. And the problem is we can't really rewrite one in terms of the other. Remember, I could rewrite sine squared in terms of cosine, but I can't rewrite sine in terms of cosine and vice versa. So in order to help us, we can actually square both sides of our equation. So as long as we're doing the same operation on both sides, it's completely legal. So this gives us cosine squared of x plus 2 cosine of x plus 1 equals sine squared of x. And now I have something that I can rewrite. So I'm going to rewrite sine squared in terms of cosine using my Pythagorean identity. So it becomes 1 minus cosine squared of x. And now it looks like something I can factor, so I'm going to set my equation equal to 0. And then this actually cancels out, so I have equals 0. And you can see from here we have a GCF of cosine of x. So cosine of x, of 2 cosine of x actually. And then this leaves us with cosine of x plus 1 equals 0. So from here, we can do our zero product property. We could say 2 cosine of x equals 0, which is just cosine of x equals 0. Cosine of x plus 1 equals 0, so the cosine of x equals -1. And now it's time to use our inverse functions. So the arc cosine of 0, knowing the domain or the range of arc cosine is 0 to pi, would be pi over 2. And the arc cosine of -1 would happen at pi. So again, here, if this value is negative, we actually have to go over to quadrant 2. Now, for this problem, if you look at the original equation, they actually give us an interval for our answers, which means we don't need to write it in a repeating way. So they just want all of the answers between and including 0 and up to 2 pi, but not including 2 pi. So here, for cosine, or for pi over 2, I know that cosine of 3 pi over 2 is also equal to 0, so that will be an additional answer here. But I know for -1, it only happens at pi in that first rotation. So here I have exactly 3 answers: pi over 2, 3 pi over 2, and pi. Now, for these, there is one last important step that we have to do. And this comes from the actual method that we're using. So when we use the method of squaring both sides, we're changing the degree of the entire equation. And whenever we use this method for any type of equation that we're solving, you might end up with extraneous solutions. So you actually do need to double check all 3 of your answers to make sure that they work. So let's try pi over 2. We're going to substitute it into our original equation. So here's the first one. So we have cosine of pi over 2 plus 1 equals the sine of pi over 2. We know that the cosine of pi over 2 is 0. So 1 equals, the sine of pi over 2 is 1. So pi over 2 is a solution. Now let's try 3 pi over 2. So here, if we do the cosine of 3 pi over 2 plus 1 equals the sine of 3 pi over 2. So here we still get 0 plus 1, but here the sine of 3 pi over 2 is -1. So in this case, 3 pi over 2 is an extraneous solution. Okay, last, let's check pi. So the cosine of pi plus 1 equals the sine of pi. So the cosine of pi would be -1, and the sine of pi is 0. And 0 does equal 0, so that is a solution. So it turns out that our only 2 answers here are pi over 2 and pi. Okay, so go ahead and pause the video and see if you can give this example a try. And please solve for the same interval that we did in the last problem. So from 0 to 2 pi. And we'll check your answers in just a few seconds. Okay, so let's check our answers. So here, if you square both sides and you rewrite cosine squared as 1 minus sine squared, you get something that can be factored in this way. So we get sine of x equals 0 and the sine of x equals -1. So within the range of 0 to 2 pi, this gives us the answers 0, pi, that's when sine is 0, and then 3 pi over 2, which is when sine is -1. So since we did square both sides, we do need to check our solutions. So if you check x equals 0, substitute in, it works. However, if you check x equals pi, you actually get 1 equals -1. So that answer is extraneous. 3 pi over 2 also works, so here we have 2 answers. Okay, so now we're going to talk about how to solve a trig equation that has multiple angles. So we're actually going to solve it just like we've been doing, and we're just going to keep this as 3x, and then we're going to solve it completely, and then our very last step will actually be to finish solving for x. So in this case, we're going to divide everything by 3. So most of what we're going to do is exactly like what we've been doing. So here I look at this one and I say I would like to isolate this trig function. Don't worry about the 3x for now. So I can add 1 and divide by 2. And from here, we would use our inverse function. So again, instead of saying x equals arc sine of 1/2, we would say 3x equals the arc sine of 1/2. So we know that 3x would be pi over 6. That's the arc sine of 1/2. But let's see where else that might be happening. So if we have pi over 6 right here, again, arc sine, this inverse function can only tell us one answer, but we know that there's other angles whose sine is positive 1/2. And the other time that occurs is at 5 pi over 6. So here's what we have. We have 3x equals pi over 6 plus 2 pi n. Again, this will reoccur every full cycle. And then we also have 3x equals 5 pi over 6 plus 2 pi n. So up to here, it's exactly how we've been solving it, but now we just have one last step. We're actually going to divide our entire answer, even this part, by 3. So here we get x equals pi over 18 plus 2 pi over 3n. And here we get x equals 5 pi over 18 plus 2 pi over 3n. So again, if you ever see a multiple angle, one way you can do these is actually just solving for 3x and then dividing your final answer by 3. All right, let's try one more together. So we're going to use that same method. We're going to actually isolate this. Don't worry about the x over 2. So here we have the tangent of x over 2 equals 1 over root 3. And it might help, maybe a more familiar form of this is root 3 over 3, because that's more similar to the values you see in the unit circle. So now we can do our inverse function. So x over 2 equals arctangent of root 3 over 3. So we know that that angle, so x over 2, is going to equal pi over 6. But we also have to figure out, well, where else could we have answers, because arctangent can really only give us one angle. So we know that tangent is also positive in quadrant 3, so this could also happen at 7 pi over 6, which you might notice it's exactly pi units apart. So it's you add pi. So we can actually just say plus pi n. Now from here, all we have to do is finish solving for x. So I'm actually going to multiply everything by 2. So that gives us x equals pi over 3 plus 2 pi n. So when we do this step, we even multiply the repeating portion by the value. And there you have it. Okay, go ahead and pause the video and give this last one a try. Okay, go ahead and check your answer here. So remember, isolate sine, use arc sine, and we get x over 3 equals negative pi over 3. Remember, the arc sine of negative root 3 over 2 is negative pi over 3. Sine is also negative in quadrant 3, so 4 pi over 3 would also be an answer. So these are going to repeat every 2 pi units, so these would be our answers, but to finish solving for x, we just multiply everything by 3. Okay, that is all for today's video. Thank you so much for watching.